Okay, hello, BC Calculus. Words quite fail when I try to describe how excited I am for this screencast. Mostly, I'm excited for you, as I always am. I'm not really excited for myself. I know this already. But if you get to the end of the screencast, and by the way, this screencast is a large part of the homework tonight. Okay, the homework is going to be quite small. I know you have a number of things in your hands: a review problem set, this screencast, and then a small homework assignment. Okay, if you get to the end of the screencast to understand kind of how everything ties together, I would say that this is probably the single best answer to the question, what really are series and infinite series in particular all about, and what really could this test be about on Friday? Okay, so this is just from your last page of that handout from in class. Okay, I'm going to pick up right here. So the polynomials that we talked about in class were nth degree polynomials. If we talk about the case where n is infinity, so to speak, because we can never really get to infinity, okay, we would then call that infinitieth degree polynomial a Maclaurin series, this word being the operative word here, okay? So we only use the word Maclaurin polynomial if I am looking at a finite degree polynomial. A Maclaurin series then is taking that polynomial out to the infinitieth degree. So if you look here, I asked you to generate the third Maclaurin for f of x equals e to the x. We did the fifth in class. You can look at it. I then said, okay, generate the Maclaurin series for f of x equals e to the x and express this infinite series in summation notation. And here is where it is. If you're using summation notation to express an infinite series or a Maclaurin series, right? What's important here is to notice that this upper limit will go to infinity, okay? The questions that were asked in class, I think it was you, Walter, or was it you, or was it Arjun? Or was it Walter asking while I was yelling at Arjun? Probably that last scenario. Walter asked the question about writing a series in summation notation. It absolutely requires that you identify a pattern first, okay? So when you look for a pattern in a Maclaurin polynomial or Maclaurin series, you're going to want to write out the first few terms of the polynomial and then look, okay, and try and find a pattern. I'll talk about that more in this screencast here. Okay, here's where we are. This is what's new for us. Well, actually, this was new for us too, the idea of a Maclaurin series. Now that we have an infinite series, we can ask this question. Find the interval of convergence, because there is no interval of convergence. There is no question about convergence of a series if it's not infinite. Let me say that again. If a series is finite, for example, then we know the series converges, because if the sum ends, then obviously it converges. When a series is an infinite series, that is when you can ask the question about the interval of convergence, okay? And to find the interval of convergence of the series, you absolutely do need to have your Maclaurin series in summation notation. If you follow my blue here, what I did was I used the ratio test for absolute convergence, making sure, just as I showed you in class, I'm very picky about all the notation here. When you do this out, you'll find that this limit of the k plus first over the kth term approaches 0, which is always less than 1 for all x. So the interval of convergence is negative infinity to positive infinity. Now, here is kind of the big point in all of this. This is the big point. As the degree of your Maclaurin polynomial approaches infinity, the Maclaurin series, right, because it's the infinite series, converges to the function you are approximating for the values of x that are in the interval of convergence, okay? So what that means graphically, and again, I'm going to just bring you to Desmos for a second so you can see something here, all right? What I've done here, just follow me in the graph, please. If you look at the red is right here. This is obviously the graph of y equals e to the x, okay? This here in blue, this is just the first degree Maclaurin polynomial, or the name we used up until this point was the line tangent to y equals e to the x at x equals 0, okay? If I take that away, this is the quadratic or degree 2 Maclaurin approximation of the function y equals e to the x. And if you compare these two, just look, right? Do you see how, if you look at this, see how the green, the parabola, is a better approximation for y equals e to the x at x equals 0 and at values of x close to x equals 0. I want you to notice something else too. Look right here. I hope you can see my cursor. You'll notice that the center, so to speak, of how closely the approximating polynomials hug y equals e to the x, right? Of course, it's centered at the point of tangency, which is right here, x equals 0. Okay, now I went ahead and I just went, this right here is the 17th degree Maclaurin polynomial. Okay, let me do it again. Here is y equals e to the x. Let me see if I can zoom out to make this, okay? Here is the degree 17 Maclaurin. Boom, there it is. Do you see it? Right here, look at that. And once again, if I scroll up here, you'll see, okay, that if you zoom in and you stay within a symmetric interval of the point in question, the two to the naked eye are almost indistinguishable, okay? The point here is this is a degree 17. Degree 17 because, as you can see here, I got tired of just plugging things in. But clearly you notice that as I look at polynomial approximations, first the linear, then the quadratic, then the degree 17, okay? It is undeniably true that the higher the degree of the Maclaurin polynomial, the better approximation of f of x at about x equals 0, okay? The point of tangency here being at x equals 0. So let's go back, and you have to write this down. I wrote a nice paragraph here. What we're saying here is graphically, you notice that as the degree of the Maclaurin polynomial increases, the polynomials kind of start to bend and morph their way, right, to resemble y equals e to the x over a larger and larger interval of x. Do you understand what that means? A larger and larger interval of x. Maybe I was being badly poetic, but what I'm saying here is just kind of look at the approximations, right? We start with our little line, then it kind of bends around and it becomes a parabola, right? And then it kind of, you know, if I wanted to, I can go do the cubic and do it in stages, but each Maclaurin polynomial, as the degree gets higher and higher, it kind of resembles y equals e to the x more and more over a larger and larger interval of x. And that interval of x is centered at x naught, which is x equals 0. So that's what I wrote here. Okay, graphically you notice that as the degree of the Maclaurin polynomial increases, the polynomials bend and morph to resemble y equals e to the x over a larger and larger interval of x. Not surprisingly, the middle of this interval is the point of tangency, x equals 0. Okay? All right, that is probably the best story that I could tell you in terms of what these mean. I have class. I'll be right back. Okay, so here I am. So yes, I did in fact have class, and because I was so engrossed in this, I was late. All right, so here is another question. Here is the function, natural log of 1 plus x. I'd like you to find the 5th degree Maclaurin for f of x equals ln of 1 plus x. Do that first, and before you proceed to part B, which asks you to find the Maclaurin series for f of x, and this series is to be expressed in expanded form and also summation notation. So do A first, and then let's do B together along with C, okay? So when you finish your A, go ahead and replay me. So here is kind of my notational work for A. I had to take several successive derivatives here, right? So what I generally do, and Kate asked this question, like, when you find the fourth derivative and fifth derivative, while you can make 5 tick marks if you want to, everyone kind of above 4 just writes a little small superscript. So here are my first, second, third, fourth, and fifth derivatives. Here is me evaluating all of those function values at 0. And then here is my 5th degree Maclaurin polynomial. Okay? All right. Now, Walter, you asked about a pattern. What if there's no pattern? Right? So I guess the first thing I'm going to do is say this, is let's go now to part B where it says find the Maclaurin series. Okay? First, what you can't do, and this always makes me laugh because one of my students back in the day did this. When you're asked to find the Maclaurin series, you can't just do this. You just can't make dots and say, see, I've written the series down. I've shown the reader this will go on forever. Yeah, you can't do that. It always makes me laugh. All right, you can't do that. Let's come down here to find the series. You need to find a pattern, obviously, okay? So to find the series, especially when you have to go and express it in summation notation, you have to find a pattern. Now, some of you, and you'll notice I knocked the 0 out of here because that first term was 0 right there, right? So some of you may see a pattern already, but sometimes, here's the important point, sometimes the pattern is obvious. Sometimes the pattern emerges more clearly after you simplify the coefficients. And by coefficients, please don't forget, coefficients are like the 1/2 right here, or the 2/3 factorial, or the negative, right? Okay. Sometimes if you do a little simplification, something nice happens. Here's what I did. I just took all those factorials and wrote them out. And if you look at this for a second, you're going to notice something, I hope. You'll notice that, let's see, well, this is just 1x squared over 2. Nothing can happen here. But 2/3 times 2 times 1, I kind of see that happening, right? 6/4 times, that kind of happens. And 24 that happens. And then when you go and simplify, look what happens. Here is your 5th degree Maclaurin, and a pattern is very clear to me now, especially if you want to go and put a 1 down below, right? And so now here's what's important. What we can do once you observe a pattern is you can now talk about generating the series, okay? So here's the series in expanded form. When you write a Maclaurin series in expanded form, there is a critical piece that you need to have, and it's right here in that first yellow box. You have to show the reader that you know what the pattern is because you generated what's called the general nth term, okay? So what do you do with this general nth term? You have to know the pattern. You also have to state to the reader what integer value of n you intend to start with. I'll be very honest with you and say most textbooks don't even mandate this. I don't believe the AP does either, but I do. When you put together the nth term, the general nth term, I need to know where you're starting with n. So what I did here was I took a look at this simplified Maclaurin polynomial. I figured out what the pattern is, and I noticed it's x to the n over n, x to the n over n, x to the n over n, if I start at 1. Now, I also notice, as you'll see, the alternating element, right? The fact that it's alternating. So I know I have to introduce an alternating element into my general nth term, and I also have to make sure that it works in terms of positive, negative, positive, negative. So I have -1 to the power of n plus 1. Had this just been -1 to the power of n, and if I was starting at n equals 1, my first term would be negative, and I don't want that to be the case because my first term here is positive, obviously. So what's key, and if you're asking about points, for example, when you're asked to find the Maclaurin series, the general nth term alone is 2 points alone, okay? just for the general nth term. And I would say if I look at this question as a whole, let's talk about this. The question as a whole, let's see, let's put some point values here just so I know you're curious, okay? Point values here would be, let's see, 5th degree Maclaurin polynomial, 5 points. Maclaurin series, it would be probably 3 to 4 points. Probably leaning towards 3. It depends on how difficult it is to observe the pattern. Then the IOC, as you know, is a 6-point question. So you're looking at one question here being between 15 and, what is this, 15 and 16 points, right? Okay, no, is that right? 14 and 18 points. Right? All right, so find the Maclaurin series. So we found the Maclaurin series. The Maclaurin series requires looking for a pattern. The Maclaurin series requires us finding the general nth term. That general nth term requires you telling the reader where you intend n to start. Then here is the Maclaurin series in summation notation. Again, note the upper limit of positive infinity. Notice here, I just chose to keep the n here. Why not, right? N equals 1. I just made these n's. You could have made these k's if you want to. That doesn't matter at all, all right? All right, find the interval of convergence of this series. And of course, if you're ever asked to find the interval of convergence, you need an infinite series to work with. Go ahead and find the interval of convergence and then replay me for the answer. Here's my work right here, looking for or using the ratio test for absolute convergence. I find the preliminary interval of convergence to be -1 to 1, not inclusive, of course. Checking the endpoints, look at my careful work here. When x equals -1, just note how these things simplify, okay? So we know this series here diverges. It's the harmonic series after all. Checking when x equals 1, right? When I plug in x equals 1, 1 to the end is just going to equal 1. So this becomes my series right here, right? And this is the alternating harmonic series, which you know converges by the AST. At the end of the day, the interval of convergence is -1 to 1, not inclusive of the left, inclusive of the right. Okay, what this means in the graphical context is that, think about that morphing behavior before, okay? What this means is in this case, as the degree of the Maclaurin polynomial increases, the Maclaurin polynomial will look more and more like, where's the original function right here? It'll look more and more like that function, but not over the interval of real numbers for x, only over the interval of -1 to 1, right? Okay, so with that, I close this screencast and I will post some written work that you will hopefully work on and make good use of over the next 2 days, and certainly when I see you on Thursday for question day. Goodbye.